We live amongst 200 billion stars. In the Milky Way galaxy, a vast cosmic city. The Earth is located in a quiet neighborhood, in a safe neck of the woods. But what if we could take our planet on a journey through the galaxy? What wonders would we see? What displays of power? What unimaginable forces? What exquisite beauty? What if we could travel through time and space to understand how our galaxy came to be and how it will end? What if we could travel on the ultimate cosmic trip and journey through the Milky Way? Many of us live in large cities. Cities which dazzle with millions of lights. But at night, those bright lights conceal something truly amazing. Turn them all off, and we're greeted with a spectacular sight: a city in the sky.
What is this? Well, this is the Milky Way. This is our galaxy. Well, if you'd like, you can think of the galaxy as a city of stars.
Our galaxy, the Milky Way, contains 200 billion stars, of which our Sun is just one. It's a vast cosmic city waiting for us to explore.
It's really a wonderful time to be an astronomer. Especially in studies of the Milky Way, we're undergoing something of a revolution. In fact, we can take you places that are really quite remarkable.
We're about to embark on an amazing journey. We'll take the Earth across thousands of light years to distant parts of the galaxy, totally different from our own. From these unfamiliar neighborhoods, our skies would appear very different. Skies with not just one, but a multitude of suns. Skies that reveal the power of stars billions of years ago, and what we might see in the future as our Sun reaches the end of its life. With the Hubble Space Telescope, astronomers are able to see billions of other galaxies. Every one is different, but there is a pattern.
When we look out to study other galaxies in the universe, we see that there are basically two types of galaxies.
Astronomers call the first type elliptical galaxies. They appear as large balls of stars, and no matter what angle they're viewed from, they always look rounded. Making up the other main class of galaxies are the spiral galaxies. Their stars are contained in arms that spiral out from their centers. Viewed across their edges, they look a bit like frisbees. So what type of galaxy is the Milky Way? The answer is written across the night sky.
The Milky Way, we believe, is a spiral galaxy. So what we're really seeing when we look up at night at this band is we're seeing our place in the universe. We're part of a giant disk of stars.
It's a disk we can only see edge on, so unfortunately we get a rather restricted view.
Now, of course, I can't show you a picture of the galaxy in all its glory. We can't fly above the galaxy and take a picture of it and show you. We're stuck in the disk of the galaxy, but we can still image it from the ground. In fact, this image is a picture of our galaxy, the Milky Way, taken from Earth.
This is one of the most detailed images of our galaxy ever created. It's made from 800 million pixels contained in over 1,000 individual photographs, taken from the darkest places on Earth. The photos have been painstakingly stitched together to create this breathtaking vista. But as impressive as it is, it's only part of the picture.
It's something like a pizza, and if you were in the pizza, if you were a pepperoni, your view would not be a very clear one of what the whole story was. In the same way, we don't see the whole reach of the Milky Way.
What astronomers really need is a bird's eye view.
You would need to get out of the Milky Way to really see what it looks like. We don't have a way to do that, but we can look at other galaxies and see what they look like.
Hubble can provide us with exquisitely detailed images of nearby galaxies, like Messier 74. It's over 30 million light-years away, but that still makes it one of our nearest neighbors. Its structure is impressively clear, a beautiful spiral galaxy with its stars contained in large arms sweeping out from a bright core.
This is an example of a galaxy that astronomers think looks a lot like our galaxy, the Milky Way. This is a great representation of our own star city. In the central region, we have the downtown. This is the bulge, this bright spot in the middle. And from that, we see spiraling out these arms, these beautiful spiral structures we see in this galaxy.
By comparing the detailed images Hubble has taken of other spiral galaxies with the best images of our own taken from the ground, and by using satellites to measure the distance and density of stars in different directions, astronomers have been able to draw a grand plan of our star city. At its heart is a bright central region. This is the galactic core. From here, two majestic spiral arms, bright bands of billions of stars, sweep outwards. They are called Scutum Centaurus and the Perseus arm. There are three smaller arms containing smaller stars. From one side to the other, our galaxy measures a staggering 600,000 trillion miles.
It takes light 100,000 years to cross our galaxy. This is a big galaxy, and it's quite amazing, if you think about it, that we understand as much as we do about this system.
So now we know where we are. Our sun and solar system are located here, in a quiet neighborhood nestled between two spiral arms. So we'll begin our journey by taking the Earth to one of the most spectacular locations in the Milky Way, a place that holds the clue to how the 200 billion stars in our galaxy, including our own sun, were first created and it's just around the corner. We're taking a ride through the Milky Way. First, we're traveling to a place where stars are born. Even at the speed of light, 186,000 miles a second, the journey lasts for 1,500 years. We've arrived at a vast glowing cloud of gas and dust, the Great Orion Nebula. With the Earth in this new neighborhood, the skies become a brilliantly illuminated cosmic canvas. But this cloud is more than just a work of art. It holds the key to how our sun and every star in the galaxy came to be. The first clues come from looking at the Milky Way from our perspective. It seems there's more here than just stars. With the naked eye, we can pick out large dark patches. Astronomers like James Bullock provide a clearer picture.
Perhaps the most beautiful part of this image is that we have this contrast of dark and light regions running through the plane of the disk. What that really is, it's dust. There are clouds of dust that are casting a shadow from the back of the stars. So the stars are trying to shine their light through. There are dust clouds there that are blocking the light, much like a cloud on Earth would block the sun.
These vast clouds of cosmic gas and dust stretch thousands of light years across the Milky Way. Hubble has spotted them in most spiral galaxies. Dark, ghostly bands woven throughout their spiral arms and spreading across their entire disks. Look closer, and there is something strange about this gas and dust. There are patches where it appears to glow. These bright glowing clouds are called nebulae. And along with the Orion Nebula, our Milky Way has some spectacular examples. The Eagle Nebula, with towering pillars up to 4 light-years in size. The Carina Nebula, a dark canvas of art hung in the blackness of space. And these vibrant colors reveal what gases nebulae are made of.
So for example, if there's oxygen gas, you get a green glow. If there's hydrogen gas, you get a red glow. So analyzing the light from a nebula turns out to be very instructive. It tells us what's there, it tells us what the physical conditions are. We can tell how dense it is, how hot it is, and what it's made of. We can find out a lot about the neighborhood by looking at these clues that come directly from the glowing gas.
The gases in these nebulae are glowing at thousands of degrees. But what's the source of the heat? To find out, we need to peer deep within.
But of course, the gas and dust is in the way. So it's not so easy. It's a very mysterious part of the galaxy. It's a place that we have to use these special tricks to look into.
Kimberly Weaver is an astrophysicist who's familiar with these tricks.
I've got a really neat way to show you this. This is a bag that you can't see through with your eye, so a normal telescope that looks at optical light could not see through this. In infrared light, a telescope can see through it. The infrared camera, if I put my hand inside, can see my hand. I'll wiggle my fingers to show you that you're seeing the heat from my hand inside the bag. And this is just like a star that's hidden inside a cloud of gas and dust that infrared astronomers can detect by using an infrared telescope. This is a picture of the Orion Nebula in visible light. We can see all of the gas here located in front of what we know are stars in the background. And we want to be able to look inside this nebula and see the stars. In infrared light, in this image, we can now pick out the stars inside the nebula. And we can see dusty cocoons around the stars.
But to learn the true significance of these stars, we need to strip away the dust altogether.
How do we get rid of all this haze and fog? The way to do that is with an X-ray picture. Now when we transition into the X-ray image, you can see just the stars themselves. The X-ray is coming from the surfaces of the stars, and now we can study them in great detail.
By analyzing the light from these stars, astronomers have made an astounding discovery. Hidden within the Orion Nebula are some of the youngest stars known, just a few 100,000 years old, a mere heartbeat in the life of the galaxy. So the Orion Nebula is a place where stars are born. And the same thing is happening in nebulae throughout the galaxy's spiral arms.
These regions are the nurseries for new stars. There are young stars in these regions that are heating up gas clouds that surround them and making those gas clouds glow pink.
Stars are made out of gas, basically, and our galaxy has gas. In fact, our galaxy, you can think of it as having an atmosphere of gas and dust that surrounds all of the stars that we see in the disk. And it's from this gas that new stars are born.
By observing nebulae at different stages in their evolution, we can piece together the story of star birth. It all starts within cold, dark clouds of dust and hydrogen gas, where a subtle tug of war begins. The cloud wants to dissipate, like smoke in air. But gravity wants to pull it together.
They're in a kind of balance between gravity pulling in and gas pressure pushing back out. Gravity wins, and the material crunches down into a disk that is the beginning of becoming a star.
As gravity pulls more and more gas towards the center of the disk, it's compressed to enormous densities, causing its temperature to soar. At 18 million degrees, a miraculous transformation takes place. Hydrogen atoms fuse together to form helium. And with a burst of nuclear energy, stars begin to shine.
These stars eventually get their nuclear fires going in the core. And when they do, they heat up, they can expel the material that's around them so that it kind of clears up the neighborhood.
Within a few million years, fierce stellar winds willow away the surrounding gas, forming spectacular contorted patterns.
It blows away the gas, it blows away the dust, and it lets us see this beautiful new thing, this place where the star has been born.
A human lifetime is too short to appreciate the wonder of star birth in the spiral arms. But hovering above our galaxy, we can speed up cosmological time, compressing millions of years to just a few seconds to witness star birth on a truly grand scale. But here and there are even more brilliant flashes of light. These are places where stars aren't being born, they're dying. They are some of the most violent and dangerous places in the galaxy. And it's here we'll travel to next. This is the Crab Nebula. Like nebulae which spawn stars, it's made of gas and dust. But that's where most similarities end. For Alex Filipenko, it represents an intriguing industrial zone within our galaxy, where the elements from which our world is made are manufactured.
Look at that molten iron. Holy moly. The Crab Nebula is a fascinating object. We see these very rapidly expanding gases.
The crab may appear static, but its gases are racing out from its center at over 3 million miles an hour. Blasted out by a phenomenally powerful event in the past. What could cause such violence?
When we examine the gases of the Crab Nebula, which are expanding outward, and we extrapolate that expansion backward in time, we find that all of the gases were at a common point about 1,000 years ago.
1,000 years ago on Earth, there were civilizations watching the heavens. In 1054 AD, Chinese manuscripts tell of the sudden arrival of a brilliant new star. It shone brighter than any other star. So brightly, it was visible during the day. Then it mysteriously disappeared. Today, the Crab Nebula appears in exactly the same part of the sky where the Chinese observed their brilliant star. What they witnessed was the moment the crab was born.
The Crab Nebula was produced by the colossal, titanic explosion of a star at the end of its life. It's a supernova remnant.
The spiral arms of our Milky Way are littered with these colorful remnants. Tombstones of stars that died violently, in cataclysmic explosions astronomers call supernovae. To understand how these calamities occur, astronomers need to catch a massive star in its death throes.
Astronomers are like detectives. We have to figure out what's going on in the universe, sometimes based on a minimal number of clues. And in the case of most astronomers, the clues come from only the light.
Andy Howell knows that catching light from a supernova is all about timing.
Supernovae happen about once every 70 years in a galaxy on average, so about the human lifetime. So chances are you're not going to see one in your lifetime. In fact, the last one in our galaxy that anybody saw was about 400 years ago. So it's been a long time, and I study supernovae for a living. I couldn't do this if I had to just wait for one in our galaxy.
Thankfully, there is no shortage of galaxies.
So what we do is we look at other galaxies, more distant galaxies. There are billions of galaxies out there.
This is a supernova that Andy and his colleagues were lucky enough to catch. An exploding star on the outskirts of a galaxy 55 million light-years away. It briefly outshone the entire galaxy. The light of 1 billion suns distilled into one dying star.
It takes supernova light 1 million or even 1 billion years to get here. They're millions or billions of light years away. But they only shine for about a month. So we have this little tiny window to study these things before that light is gone forever.
It's so critical that in the workshop, Andy and his team are preparing to survey as much of the sky as possible.
We're building a network of telescopes so that we can study supernovae in greater numbers, in greater detail than we've ever been able to before.
Once they've caught the light of a dying star with their state-of-the-art telescopes, the detective work can begin.
We collect that light and we analyze it in great detail in order to determine what's going on. What's the chemical makeup of the star? What's the pressure inside? What's the temperature? What kind of nuclear reactions are going on? How does a star explode? All of these things we figured out through the analysis of light.
In doing so, astronomers have discovered that it's only stars with a huge mass that go out with a bang.
A massive star has a very interesting and vigorous life. Initially, it fuses hydrogen to form helium, and that produces energy. That makes the star shine. Then the ashes of that reaction, the helium, fuse together to form carbon and oxygen, releasing yet more energy. Then the carbon and oxygen can fuse into still heavier elements, magnesium and sodium and neon and things like that. And then silicon and sulfur, and finally iron.
When it starts to make iron, the giant star is doomed. In the core, there's a fierce battle. Energy is pushing outwards, holding it up, while gravity wants to crush it inwards. The battle continues as the star makes heavier and heavier elements, producing energy, fending off total collapse. But once it starts to form iron, the battle is lost.
Fusion of iron nuclei into heavier things does not release energy, it absorbs energy. So an iron core builds up, but finally it becomes so massive that gravity wins. The iron core collapses. In less than a second, the outer layers collapse inward, then rebound and get blown to smithereens.
But what spells death for the star is vital for the life of our galaxy.
We're at a foundry here, and they're pouring molten iron from old machinery, and they're going to make parts for new machines out of that iron, so they're recycling it. But all that iron was created and ejected into the cosmos by gigantic stars that exploded as supernovae. Those explosions created the iron, ejected it into the cosmos, and then it got incorporated into planetary systems like ours. But ultimately, the atoms of iron were created by exploding stars.
Supernovae are the industrial zones of our star city. Cosmic foundries in which the chemistry of the heavens forges new elements.
It's fascinating to realize that the heavy elements in our bodies, the carbon in our cells, the calcium in our bones, the oxygen that we breathe, the iron in our red blood cells, all of those heavy elements were synthesized, created through nuclear reactions in stars, and ejected into the cosmos by supernovae.
Only some stars are massive enough to die as supernovae. Most, like our Sun, suffer a more gentle death.
Most stars don't die in a cataclysmic explosion. Our own Sun, for example, a typical star, will die with a whimper, not a bang.
The death of most stars occurs when the battle between gravity pulling in and nuclear energy pushing out is won, not by gravity, but by the nuclear energy. This is what will happen inside our sun when it dies.
In about 4 or 5 billion years, it'll grow into a much bigger star, a star called a red giant. And the outer atmosphere of gases will be held so loosely by the sun at that time that the gases will be blown away gently in what I call a cosmic burp.
The remains of these cosmic burps also litter our galaxy's spiral arms. Stars that die by shedding layers of elements.
Some layers are oxygen, and some layers are silicon, and some layers are sulfur. And those are the different colors we see in the Hubble Space Telescope images.
Not far from our sun is a place where a star is dying. The Helix Nebula. It gives a spectacular insight into how most stars end their lives. Our sun is destined to create a similar vista when it too dies 5 billion years from now. But this doesn't happen in every neighborhood. At the center of the galaxy is a place of mystery where stars disappear altogether. It's here we'll venture next. On the next stage of our journey through the Milky Way, we're heading to the center of our galaxy.
If we were to take a trip from the spiral arms out where we are by the sun down to the center of the galaxy, it would be an interesting trip. It would be very much like moving from the suburbs into the heart of a very busy metropolitan area.
As we get towards the heart of the Milky Way, the number of stars increases.
So the density of stars is tremendous at the center of the galaxy. It's about 1 billion times higher than out here by the sun.
Here, at the center of the galaxy, there are so many bright stars in the sky that the Earth is bathed in perpetual light. It's a stunning location, but it's also mysterious. These stars are not just close together, they're on the move at enormous speeds.
Going to the heart of the galaxy might not be dissimilar to going to an amusement park. The rides are somewhat similar to how the stars orbit the center of the galaxy. 10 million miles per hour compared to, say, our sun is about a factor of 50 times faster. So something has to be going on at the center of our galaxy to make that happen.
The heart of our galaxy lies 26,000 light-years away. It's difficult to observe through the vast amounts of stars, gas, and dust. And there's something else which obscures the view: the Earth's atmosphere. By measuring how a laser beam is distorted in moving air, it's possible to compensate for the atmosphere's blurring effect, a process called adaptive optics.
So let me show you an example of how powerful adaptive optics is. The stars that we want to see are the ones that are at the very center. We think the heart of the galaxy is right within the center of this box, which is panned out here. Without adaptive optics, this region looks completely blurry. You don't see the individual stars. With adaptive optics, you see the individual stars.
For 15 years, Andrea has been taking infrared images of the stars at the center of the galaxy to produce an extraordinary time-lapse film.
So if we zoom into the very heart of the galaxy, we can actually see the data that we've taken over the last 15 years, and you can see the stars, and you can see the tremendous motion that they've gone through. In particular, SO2, which is my favorite star. Every astronomer has a favorite one. So you can see SO2 goes around, and in particular, you can see as it gets to the center of the frame, it moves much more quickly. So something's interesting as it goes through that region. So putting everything together, all the measurements that we've made, we've been able to make an animation that shows how the stars have moved over the course of 15 years. Each star goes whipping around the center of the galaxy. In particular, the most striking thing that you'll notice is the motion of SO2. So SO2 goes on an incredible roller coaster ride. It comes whipping around and then back out.
Something with a tremendous gravitational pull sends SO2 on a rapid orbit around the center of the galaxy. Something with a huge mass.
SO2 goes around once every 15 years, and what it tells us is that there is 4 million times the mass of the Sun confined within its orbit.
And astronomers know of only one contender for something that has such a giant mass and is so small.
So that's an incredible amount of mass inside a very small volume, and that's the key to proving a black hole.
So at the center of our galaxy lies a massive black hole, an object whose gravity is so strong that not even light can escape it. This is an image of the center of our galaxy. We can't see the black hole, but we can see bright clouds of gas and dust spiraling towards it. We're nearing the black hole. It's at the center of a stream of dust and gas. The entrails of stars, shredded after straying too close.
Black holes grow with time, and that happens by material falling onto it, accreting onto it. And that material can come in the form of either gas or stars that get torn apart by the black hole itself.
At the center is the invisible black hole. What we're seeing is material it's feeding on. The glowing region is the accretion disk. Star debris falling inward, whipped around in the maelstrom, heated by friction to such high temperatures that it glows white hot.
So at the center of our galaxy, we do have a black hole. We now know that today, but it's not producing a tremendous amount of energy. So it's perhaps, we could say, it's a black hole that's on a diet. It simply doesn't have a lot of material to feast on.
But what would happen if SO2 and the other stars were pulled inward by the black hole?
What happens when that material falls onto the black hole is that the black hole, there's radiation associated with the black hole, and it can generate these jets squirting out from the center of the galaxy.
Spewing out subatomic particles close to the speed of light, the beams are like vast cosmic searchlights. This is Messier 87, a large elliptical galaxy which has a supermassive black hole at its heart that's feasting on its own stars. Shooting out from its bright core are jets which travel over 5,000 light years.
I like to call these the prima donnas of the galaxy world. These are the 10% of galaxies that are show-offs.
Astronomers believe that the massive black hole at the heart of our galaxy has always been there, right from the beginning. But just how old is the Milky Way galaxy? To find out, we need to leave the disk altogether in search of our star city's oldest neighborhoods. We're traveling upwards, away from our solar system, out of the spiral arms of the Milky Way. In front of us lie vast clusters of stars, satellite groups that orbit the heart of our galaxy. These are globular clusters. Over 150 have been discovered. Here, astronomers have found the answer to one of the greatest questions in astronomy. How long has our galaxy existed?
Globular clusters are really fascinating groups of stars. They contain about 1 million stars each. And the thing that's really cool about them is the stars are really tightly packed.
If you could visit a globular cluster, the night sky would be spectacular, where many of the stars would be as bright as the full moon.
And the nighttime sky in all directions would be filled with bright nearby stars. There'd be like fireworks all the time.
Apart from their sheer number, there is something intriguing about the stars found in these clusters.
One of the very interesting aspects of globular clusters is there's no sign of young stars.
Stars are a bit like people. Look at them and you can guess their age and the life they've lived. With people, it might be grey hairs or wrinkles. With stars, it's their colour and their size.
So the biggest stars, the most massive stars, the ones with the most gas, live life in the fast lane. They live very short amounts of time, but they burn very brightly, and they're very, very hot, and so they tend to be blue.
On the other hand, you have the red stars, which use their energy very conservatively, last for a long time, don't glow too brightly, and those stars last for a very long time.
So by measuring the brightnesses and the colors of the stars in a globular cluster, we can figure out how old they are. And here's the remarkable thing. They're very old. Globular clusters, at least the stars in globular clusters, in many cases are almost as old as the universe itself.
Globular clusters are like living fossils. It's like discovering a community of people who've been around since the Stone Age. Some stars here have been shining for 12 billion years, more than twice as long as the Sun. And that helps to put an age to the Milky Way.
Globular clusters are part of our galaxy. They orbit our galaxy. In some sense, they're tracers of our galaxy itself. And so by the fact that the globular clusters are so old, it suggests that the galaxy is old.
So globular clusters tell us something extraordinary. Our galaxy is one of the oldest objects in the cosmos. It's been around almost since the beginning of the universe, at least 12 billion years. The stars in these clusters also reveal that when it first formed, the chemistry of the galaxy was very different from how it is today.
We can measure the chemical properties of those stars. Turns out they have very low abundances of the heavy elements. Things like iron are very rare in globular cluster stars compared to a star like the Sun.
What's true of globular clusters is true of the early galaxy. It would have been a far less colourful place, lacking heavy elements which colour the nebulae and supernovae remnants we see today. But more importantly, it would have been a galaxy without life. It took billions of years for stars to form enough heavy elements for the evolution of life to begin anywhere in the Milky Way. But that poses another profound question. How has the galaxy managed to keep going for so long?
One of the puzzles about our galaxy is that we know that it's had stars forming continuously for about the last 10 billion years. But at the rate it's eating up its gas now, it's forming new stars, it should burn out that gas soon. It should run out of fuel. And so there has to be some source for new fuel.
That source must be beyond the galaxy. And recently, astronomers have made an astounding discovery. Globular clusters are not the only groups of stars orbiting the Milky Way. There are also ultra-faint dwarf galaxies.
The reason why we haven't known about these dwarf galaxies for very long, these so-called ultra-faint dwarf galaxies, is that they contained just a few hundred stars, 1,000 stars. So you try to find a clump of 1,000 stars while looking through a mass of 1 billion stars. It's not easy. This is a needle in a haystack problem. And it's only because we have the precise maps, it's the precision of modern astronomy that's allowed us to discover these extremely interesting dwarf galaxies.
They may be elusive, but they can help to solve the mystery of what's fueling the galaxy.
So these dwarf galaxies are whizzing around our galaxy. They're in orbit around it. Now, sometimes they get too close, and when they get too close, they get ripped apart. In fact, they get eaten, in some sense, by our galaxy.
This computer model shows dwarf galaxies as colored disks. Over time, our galaxy at the center devours many of them, pulled in by gravity, supplying more gas and dust from which new stars will eventually form.
So in much the same way that a large city might sort of cannibalize its neighbors, the Milky Way is cannibalizing its dwarf galaxy population.
Globular clusters and dwarf galaxies give an insight as to how old our galaxy is and how it's survived for so long. They were once thought to mark the outer limits, but today astronomers believe the Milky Way galaxy is much bigger than what we can see. To understand why, we'll travel to the stars of the outer galactic disk. Far from our usual place in space, we approach the edges of the galaxy, where we may be able to discover what holds all the stars together to make our Milky Way. Here, our night sky looks a little different. The Milky Way is smaller, and the sky is darker. But even though we're tens of thousands of light years further away from the center of our galaxy, we're still bound to it by the force of gravity.
Gravity is the force that makes any two objects want to move towards each other.
On Earth, cities are built from iron girders and concrete beams. This largely invisible scaffold holds these buildings up against the pull of gravity. Without this scaffolding, the skyscrapers would crumble and the bridges would collapse. But gravity not only governs us on Earth, it governs throughout the universe. Its laws are straightforward. Anything that has mass has a gravitational pull. The greater the mass, the stronger the pull. With 200 billion stars, the Milky Way has a huge mass and a tremendous gravitational attraction. So, like buildings, our galaxy also needs propping up against the force of gravity.
Imagine the disk of our galaxy. If you just took a disk of stars and put it there, gravity would tend to make this disk collapse in on itself, and it would immediately just fall together. That's not what we see with the galaxy. What's actually going on is the stars are orbiting around the center, and that's what keeps them from falling in much the same way that the Earth is orbiting around the sun.
The planets in our solar system are in a delicate balance between gravity pulling them towards the sun and their orbital velocity wanting to pull them outwards into space. To keep in balance, planets further from the sun must orbit more slowly.
If you go to more distant planets at the edge of the solar system, they're going around the sun much more slowly than the Earth is, and that's because the gravity is weaker there.
The same holds true for stars in the Milky Way. All of them are orbiting the center of the galaxy. But the stars in the outer arm should be traveling more slowly than those closer to the galaxy's heart.
What's interesting is that's not what's going on. The stars in the outer parts of the galaxy are spinning around just as quickly as those in the inner parts.
And they're not the only ones.
It's not just our galaxy, it's every galaxy we look at. Every galaxy we look at seems to be spinning too fast in its outer parts.
These speeding stars should be flung out of the galaxy altogether, but they're not.
That is a puzzle. This means that there's a lot more mass there that we just can't see.
It's this mass that must produce the gravity that holds these stars in their orbits. But when astronomers look for the mass, there appears to be nothing there. It's led cosmologists like Joel Primark to an astounding conclusion.
All of the galaxies, all of the stars and gas and dust and planets and everything else that we can see with our greatest telescopes represent about 0.5% of what's actually out there. The rest is invisible. It's mostly some mysterious substance that we call dark matter.
You can't see dark matter. The reason why you can see normal matter is because light shines on it and reflects off of it. That's how you can see me. Dark matter doesn't work that way. The light goes right through the dark matter. The way we detect dark matter is because it has mass. Anything with mass affects other things via gravity. That's the golden rule of mass. That's what mass does. It tugs on other things because of gravity.
Without dark matter, the Milky Way couldn't exist.
So the galaxy is spinning. The galaxy is spinning fairly rapidly. The reason why it can spin so rapidly is because it has so much dark matter. The dark matter has a lot of mass, and therefore it has a lot of gravity, and that's what keeps the stars whizzing around. If you were to magically take all of the dark matter away from our galaxy, it would fly apart. The stars would just keep going straight, and in a very short amount of time, the galaxy would just be gone.
There'd be just a mess of stuff flying every which way. And that's not just true of our galaxy, it's true of every galaxy and every cluster of galaxies in the universe. They're all held together by this invisible stuff that we call dark matter.
So we need the dark matter. It's the glue that holds galaxies together.
The discovery of dark matter has revolutionized our picture of the Milky Way. The stars of the galaxy represent just a fraction of its mass. The rest is made up of an invisible halo of dark matter. It surrounds you, me, and every single star.
The stars are just the central region. The halo is at least 10 times bigger and weighs much more than 10 times more than all the stars and gas and dust that we can see. It's that whole structure that's the real Milky Way galaxy. And that's not just true of our galaxy, it's true of every galaxy we've ever studied.
But dark matter does more than simply hold galaxies like ours together. Astronomers think it binds the Milky Way into an extraordinary structure along with billions of other galaxies. To explore it, we'll take a journey to the very edge of the universe. We're leaving the galaxy altogether, on a journey that will take us across billions of light years of space and billions of years of time.
One of the great things about telescopes is they're time machines. Because light travels at a finite speed, when we look at distant objects, we see them as they were when the light left them.
As astronomers look back over billions of years, they see a universe teeming with galaxies. But the extraordinary thing is that galaxies are not scattered randomly through space. They cluster along delicate filaments, forming a vast cosmic web. So what gives the universe this intricate structure? And what does it have to do with the birth of galaxies themselves? The answer is shrouded in darkness. Look back far enough, and gradually, all the galaxies disappear. We've reached a mysterious period of time, 12.5 billion years ago.
There's this time period that we can't see because nothing's formed yet. It's this epoch that's called the Dark Ages.
During the Dark Ages, the universe was a very different place from the one we live in today. Back then, it was filled with dense clouds of hydrogen gas. Like the gas that obscures the stars in the Milky Way today, these clouds block what might lie within.
It's extremely frustrating because this region, this time period, holds within it, in some sense, the Rosetta Stone of galaxy formation.
But there are clues as to what was happening inside those dense hydrogen clouds. Look back even further in time to a moment just 380,000 years after the Big Bang, and the universe was filled not with darkness, but with light. Its faint afterglow is still visible to astronomers today.
In fact, this picture is amazing. This is a picture of the early universe. This is an image of the afterglow of the Big Bang.
At this time, the universe was the same everywhere, filled with a hot atmosphere of matter and radiation. But the seeds of the very different universe we see today had already been sown.
Everywhere we look around us in the universe, we see structure. We see galaxies all over the place. Where do these galaxies come from? There's a big clue to this buried in this picture. If you look closely, you can see that there are red spots and there are blue spots. These red regions are regions where there's basically more stuff. And the blue regions are the regions where there's less stuff.
This image reveals that there were tiny variations in the density of the gas which filled the early universe. Minute ripples that would grow with time.
We think that these ripples, these primordial ripples, are the seeds to all future structure. These ripples eventually grew into what became the first galaxies.
But how could something so small grow into something so big?
It's gravity that amplifies these ripples. And in fact, we need an additional source of gravity to amplify those ripples to form galaxies like we see today. And that additional gravity comes in the form of dark matter.
What happens is that first the dark matter forms the structure. The ordinary matter then follows the dark matter. The ordinary matter is hydrogen and helium at this stage. And the hydrogen and helium fall to the center of the dark matter halos that are forming, and that's going to become the galaxies.
If these ideas are right, then the link between these minute ripples in the early universe and the vast cosmic web that now fills space is dark matter. But of course, dark matter is invisible. So there is no way to see it creating the cosmic web. But it is possible to simulate the process using one of the world's most powerful supercomputers.
Here we are at NASA Ames, the research center where we have the Pleiades supercomputer. Each one of these cabinets contains 512 processors. Let me show you. So that's half a terabyte in each one of these cabinets. There's 110 of these cabinets to make up the entire Pleiades supercomputer. So this is a really big supercomputer. This is NASA's biggest.
The challenge is to develop a virtual universe from its early beginnings to the present day to see what role dark matter might have played in shaping the cosmos. If you tried to do this using a home computer, it would take almost 700 years.
If we're doing our job right, we can put the pictures into a video, if you like, that shows the whole structure of the universe.
And this is the end result. It's called Bolshoi, an amazing visualization of what the structure of dark matter might look like in the universe today.
So what we're looking at is a region about 200 million light years across, which is actually just a small part of our really big simulation that we call Bolshoi, which is Russian for big. Everything that you see here is actually completely invisible. It's not the visible universe that you're seeing. The bright spots are dark matter. They're the halos of dark matter within which galaxies form. And each one of these little blobs would represent probably one or at most a couple of Milky Way-sized galaxies. And you can see that the galaxies are in long chains, filaments we call them. Basically, all the structure is forming along these filaments of dark matter.
For Joel, the acid test is to compare the dark matter structure Bolshoi predicts with the real thing, the structure of galaxies seen in the universe.
As far as we can tell, these simulated universes that we make in the supercomputers look just like the observed universe. There don't seem to be any discrepancies at all. This is exactly the way we see the galaxies distributed in the observed universe.
Bolshoi's simulations are incredible. They perfectly match the pattern of galaxies seen in the cosmos today. It's persuasive evidence that dark matter has been sculpting the universe for billions of years.
No, I'm really impressed with this, because we stuck our necks way out when we made these first predictions. And they turned out to be right, and they keep turning out to be right. And, you know, this is, of course, great joy for a theorist.
By going back to the beginning of the universe, astronomers have uncovered the origin of the structure of the universe. But our time traveling isn't yet over. There is still the question of how the first galaxies kindled the very first stars. We're on a journey visiting the Dark Ages, a time over 12.5 billion years ago. The sight is spectacular. The sky is ablaze with the first stars of the Milky Way, their light piercing the fog, bathing us in a strong ultraviolet energy. These first stars will change the way we see the universe forever. Tom Abel has modelled their lives and their deaths.
The beautiful thing is that we now have computers. We program them with the laws of physics. Put in some gravity, hydrodynamics, how gases move around, some of the chemistry. And as we evolve it all together, we gain an intuition of how stars come about. And in the case of the very first stars, this is absolutely crucial.
It's cosmic cookery. Tom takes the basic ingredients available during the Dark Ages, hydrogen, helium, dark matter, and gravity, and sets the computers simmering. From the models, Tom can recreate the lives of these stars.
Here we see one of the first stars in the universe. It's 100 times as massive as the sun, 1,000,000 times as bright.
The first stars are huge, swollen by the massive amounts of hydrogen gas pulled in by the gravitational force of dark matter.
And so even though they have all this fuel to burn, you'd think they could live for a long time, they run through it so quickly that even after a few million years, they're already dead.
The first stars in our Milky Way were fearsome, high-octane stars, burning their hydrogen fuel at tremendous rates, rushing through their life cycle.
They like the rock stars. They live fast and die young. They run through that fuel very quickly, and even after just a few million years, they already die.
They died in some of the most violent explosions to rock the universe. Gigantic supernovae which shone brilliantly. And the energy given off from the life and death of these massive stars led to a remarkable transformation.
In the first billion years of the universe history, galaxies start to form in a dark hydrogen fog, their light not being able to get to us. But as time progresses and their most massive stars put out ultraviolet radiation, it's that radiation itself that changes the fog around them. And the universe becomes transparent in those regions. These galaxies in here clearing out the fog around them.
The blue voids are where energy from the new stars is clearing the dark hydrogen fog.
But towards a billion years after the Big Bang, the entire fog has cleared, and we now see all the galaxies and the Dark Ages end.
As the hydrogen fog lifts, we get our first glimpse of fledgling galaxies, of which our Milky Way is one. But what does it look like?
This remarkable image is the Hubble Ultra Deep Field. It's the longest exposure that's ever been taken with the Hubble Space Telescope. It's a truly remarkable image, probably the most famous to professional astronomers.
For over 11 days, Hubble stared at a tiny patch of sky about the width of a penny held 75 feet away. And every faint smudge of light you're looking at is a galaxy. For Richard Ellis, it's a galactic treasure trove.
So much like an archaeologist would piece together history by digging into deeper and deeper layers, so a cosmologist like myself uses this image to look at the history of the universe, how the most distant galaxies, seen as they were a long time ago, evolve and grow to the bigger systems that we see around us today.
The image reveals something very intriguing about the beginning of our Milky Way.
When we look at these early galaxies, they don't resemble the star cities that we see today. They're lumpy, they're irregular, they appear to be interacting with their neighbors, they're physically very, very small. So clearly the universe was very different in those early times.
12 billion years ago, the universe was a much smaller place. It hadn't expanded to the size it is today. Our Milky Way would have been jostling for room.
So it's very difficult for these early galaxies to establish themselves. These early galaxies are struggling to survive at this very early time.
It was a case of survival of the fittest, the largest galaxies growing bigger by devouring the smallest.
So it's tough for these early systems to form, but clearly they do, and they eventually merge with their neighbors and form the bigger systems that we see today.
It was collisions in the early universe that created the beautiful spiral galaxy we live in today. But astronomers believe there's one final collision in store for the Milky Way. One which will change it forever. We've transported the Earth 3 billion years into the future. The sky is dominated by a massive galaxy called Andromeda. The view looks peaceful enough. But what's about to happen is one of the greatest calamities in the universe. The clues lie in these mysterious Hubble images. They show a type of galaxy unlike any other. They appear distorted, deformed. To understand what these mysterious objects represent, astronomers have turned to computers.
What we do is we make galaxies that look just like the Milky Way and similar galaxies. And we let them evolve in the computer. They develop the spiral structure. They look quite realistic. We then put them on a collision path.
Freeze-frame these simulations and match them with real images, and suddenly the picture becomes clear. We're looking at the greatest clashes in the cosmos. Galaxies in collision. Like cities, galaxies tend to cluster. Our Milky Way belongs to one called the Local Group, made of at least 50 galaxies. The largest in the pack is Andromeda, a spiral galaxy even bigger than ours. Today, Andromeda lies 2.5 billion light-years away. But astronomers like Abraham Lowe know that distance is closing.
When I started working in astrophysics, I noticed that most of my colleagues are thinking about other galaxies interacting with each other, colliding with each other, and I was wondering, why aren't they examining the future of the Milky Way and the Andromeda Galaxy as they will come together?
Is the writing on the wall for our star city?
Our galaxy is rushing toward the great galaxy in Andromeda. They're rushing toward each other. And they're going to encounter each other in a couple billion years.
Abraham and his colleagues decide to try to simulate this clash of the titans.
This was the first simulation of its kind. Initially, the two galaxies plunge through each other, producing these beautiful tails of stars due to the force of gravity. They run away, turn around, and come back together to make one big spheroid of stars, which I called the Milkomeda Galaxy.
The merger of the Milky Way and Andromeda galaxies. The coming together of almost 1 trillion stars.
The beautiful spiral structure of our Milky Way galaxy is not something that's going to last forever. It's going to be a mess for a while. The collision will not be one in which these two things are destroyed, but it is one where the gas in each system will collide with the gas in the other, that it'll have a burst of star formation.
And the formation of these new stars will mark the rebirth of a new galaxy.
This spectacular Hubble image shows the antennae galaxies, a grand cosmic collision between two spiral star cities. The galaxies are undergoing a frenzy of starbirth, visible as a multitude of brilliantly illuminated pink nebulae, a final flare of stellar activity before the galaxies merge to become one. This is the fate that awaits our Milky Way when it merges with Andromeda 3 billion years from now.
When they collide, there will be a lot of new star formation that takes place. There will be a kind of rejuvenation of the Milky Way for a little while, and then eventually this combined system will settle down to become a new thing, probably a bigger galaxy than either of the galaxies out of which it was made.
But the real surprise is the shape of this new galaxy.
A new galaxy is formed where instead of the disks that the original galaxies had, where all the stars are going around more or less in a plane, instead, the stars are going every which way, just like the elliptical galaxies that we see. And so we're pretty sure that this process must be a large part of how elliptical galaxies form.
The collision of the Milky Way with Andromeda will leave behind a giant elliptical galaxy. Before that happens, there will be one last sight to savor.
The image of Andromeda will be stretched across the sky, looming as big as the Milky Way itself. And it's conceivable that there would be human beings like ourselves looking at the sky and seeing this spectacular image.
But would we be the only ones? Or is the galaxy home to other civilizations? It's time for the final leg of our journey as we search for life inside the Milky Way. There are around 200 billion stars in our galaxy, but there is only one neighborhood that we know for sure sustains life.
The sun powers almost everything here on the Earth. It's the energy source, it's the engine of life and many other processes. And life here on Earth is based heavily on water. And it's liquid water that's the key to life as we know it. And it's because liquid water serves as the solvent, the cocktail mixer for the biochemistry of life.
The Earth is the only planet in the solar system with abundant liquid water. And as Jeff Marcy knows, that's down to location, the Earth's distance from the Sun.
Venus is closer to the Sun. Mars is farther from the Sun. And there's a zone in between the blazing hot furnace of Venus, the frigid Mars. That zone in between we call the habitable zone, and the Earth lies smack in that thing, where water would be in liquid form, not in steam, too hot, not in ice form, too cold, but rather a temperature that, as Goldilocks said, is just right for life.
The location of this habitable green zone depends on the star. With hot blue stars, the green zone is further out. With cooler red stars, it's closer in. Every star in the Milky Way must have a habitable zone. The question is, do they also have planets within them?
In 1995, something happened that was extraordinary. I got a call from my collaborator, Paul Butler, and all he said was, "Jeff, come over here." And it was a moment that I will never forget. I was silent, Paul was silent, and we were just stunned. There on the computer screen, I saw the unmistakable signature of a planet.
Jeff had discovered the first planet around another star. But he couldn't actually see it because the planet itself was too small and dim.
Any planet orbiting a star is lost in the glare of that host star that outshines it by a factor of 1 billion. And so instead, to detect planets, we watch the stars. And in fact, a star will wobble in space because it's yanked on gravitationally by the planet or planets orbiting that star. And by watching the star alone, we can determine whether the star has planets and how far out those planets are from the host star.
So far, astronomers have found over 400 planets around stars in our galaxy. But none seem to be in habitable zones.
One type of giant planet orbits very close to its star. We call them hot Jupiters because these Jupiter-like planets are so close that they're blowtorched by the intense heat from the star. The other sort of planet we've found is also bizarre. We've found planets that orbit in elongated orbits, elliptical, stretched out orbits, but then the planets go very far from the star where they would be quite cold. And so the planets that we've found so far are a little too weird for us to imagine that life would have a good chance of surviving.
Power on. External.
But all that may be about to change. Recently, NASA launched a powerful new telescope called Kepler, on the hunt for Earth-sized planets which may orbit in habitable zones around nearby stars.
Kepler works in the most simple way. All Kepler does is monitor the brightness of 100,000 stars with such exquisite precision that it would detect a planet as small as an Earth-like one as it blocks the starlight.
We see the same thing from Earth when Venus and Mercury are silhouetted against the Sun. But Kepler's task is far more difficult.
It's a little bit like having a searchlight in which you're trying to detect any dust on that searchlight by noticing a dimming of the searchlight when one dust particle falls on this massive searchlight.
From this tiny dimming, the size of a planet can be measured. And more importantly, together with the way it causes its host star to wobble, Jeff can work out its density.
And of course, this is glorious, because by these measurements, we'll be able to distinguish gaseous planets, probably not suitable for life, from the rocky planets that may have a surface covered by liquid water.
Astronomers like Seth Shostak aren't sure how many planets Kepler will find. But with 200 billion stars in the Milky Way, surely the galaxy is teeming with them.
You know, the indications are a lot of those stars have planets, maybe half of them do. And since planets, you know, being like kittens, you don't just get one, you get a couple. They're probably on the order of a million planets out there.
1 trillion planets, an unimaginably large number. But what are the chances of any of them being in a location where life could flourish?
We can expand the idea of a habitable zone around a star to a habitable zone within our entire Milky Way galaxy.
On our journey around the Milky Way, we've learned a great deal to help in the search for a galactic habitable zone, a safe haven for life.
In close, at the hub, there's an extraordinary amount of X-rays, harsh radio waves, even gamma rays, that would certainly destroy fragile, single-celled life just getting a start toward evolution.
Downtown is dangerous. There's a supermassive black hole down there. You get too close to that, all sorts of bad things can happen. There's also a lot of stars down there, and you know, a lot of stars sounds good. But on the other hand, if you have too many nearby stars, they tend to shake up all the comets in your solar system. They're constantly pummeling you with these collisions that, just ask the dinosaurs, are not always good for you.
Safer neighborhoods may be found in the spiral arms, but here too it's all about location.
If you happen to be on a planet near a supernova, that explosion could ruin your whole day. Life might get started, and then, you know, another couple 100 million years later, it gets wiped out. So these areas are sort of no-go zones, no man's land, well, no alien's land, perhaps.
The outer reaches of our Milky Way are quieter, but even here, life would find it difficult to evolve.
At the outskirts of our Milky Way galaxy, there aren't very many heavy elements of which the cells of our bodies and life as we know it are composed, and so we may not have the essential building blocks of life at the outer edges of our own Milky Way.
So it's no accident that we are where we are. Our neighborhood, tucked away between two spiral arms, is the perfect habitable zone, because it's remained relatively unchanged for billions of years, giving life time to establish and evolve. Other advanced civilizations, if they exist, are likely to live in similar neighborhoods, cocooned from the dangers of the galaxy. We've yet to find them, of course. But the galaxy's a big place.
We haven't found any life elsewhere. We haven't found pond scum. We haven't found dead pond scum anywhere else, not convincingly. And why is that? Well, fewer than 1,000 stars have been looked at carefully for planets that might have intelligent life. So, you know, it's sort of like going to Africa looking for megafauna, you know, elephants, giraffes, something like that. And you land in Africa and you look at the first square yard of real estate there and you say, no elephants here, and you give up. Well, we shouldn't give up. We're just beginning.
Don't miss Who Sank the Bismarck, a brand new investigation into the sinking of the infamous Nazi warship on Tuesday at 9. Next tonight, we're hunting for aliens.